In lesson 9.3 here, we're going to look at graphing rational functions. First of all, let's define what a rational function is. It is a fractional function in which the numerator and denominator are both polynomials, which usually involves having a variable in both of them, sometimes only in the bottom, but for sure in the denominator. Many times it'll be both in the numerator and the denominator. These are some examples of what the graph of a rational function, when we do some graphing here, are going to look like. It could be linear, like the one on the left here, with a hole in it, and we'll talk about what produces a hole. Okay, there's a hole at x equals -2. If you notice, the x value right here is -2. The hole is actually occurring at -2, -4, but if we notice, the x value is -2, so that's what we're stating there. Or you could have rational functions that look like the one on the right here, okay, and we actually have what are called asymptotes occurring. We have vertical and we have horizontal, and we'll talk about what creates those here and look at some examples as we go through the lesson. But if you notice, this graph is of two curves. It's actually called a hyperbola. So we can get a graph of rational function to be a hyperbola. Notice if I draw the vertical line here at x equals -2, that's the equation of that line. Notice those two blue curves do not cross that line. So there is a vertical asymptote at x equals -2. Notice the two curves never cross the x-axis. So if I think about this line right here, which is actually the equation y equals 0. Remember, horizontal lines are y equals a number. Vertical lines are x equals a number. And we'll look at examples of what produces them given certain types of functions. So just a little informational stuff there. All right, some more informational stuff. A hole or point of discontinuity occurs in the graph when there's a common factor, top and the bottom, in the rational function. And it's a common factor that actually cancels, and we'll look at some examples here in a second, but a common factor. So like you might have an x plus 1 in parentheses factor that cancels out, which means, and it's actually what causes that to be 0. The hole occurs at whatever causes that to be 0. Kind of think of it like the zero product property we did with quadratics. A vertical asymptote definition is a vertical line that the graph gets close to but never touches. Occurs when the function is written in simplest form and is undefined, and that is right here when the denominator is equal to 0. Okay, what makes the denominator 0 when it's in simplest form? That's when a vertical asymptote is going to occur. A horizontal one is a line that your graph may cross but gets close to as far as you go to the right or as far to the left. So you're going basically to -infinity with the x's to the left in the negative direction, or to positive infinity. It gets close to but never crosses. Okay, a horizontal. That can occur in some rational functions. And basically, we'll look at how to find that as we get into the specific examples here. All right, so these two examples. Determine the equations of any vertical asymptotes and the values of x for any holes in the graph. What you want to do is you want to factor anything top and bottom. We've got a factor. So what we're going to do is we're going to look at this rational function. Notice it's got variables top and bottom. Okay. On the top, this is called, right here, a difference of two squares. Okay. X squared is a perfect square, 4 is a perfect square, it's a difference. And again, a reminder, we've done a lot of difference of two squares factoring. That factors into x plus 2 and x minus 2. You square x to get x squared, that goes in the first spot. You square 2 to get 4. Okay, the minus plus signs cancel each other out, that's why there's no x term. The bottom, if you think about all your factoring rules, Okay, this is trinomial factoring, three-term factoring. I want factors of 6 that add to 5. Okay, factors of 6 that add to 5. 1 and 6, well, they add to 7. But 2 and 3 add to 5, so one of these is a plus 2, and one is a plus 3. So there's how the top and bottom factor. So that's kind of the first step you want to do. Now, if you notice, those factors can cancel, kind of like what we did earlier where factors were canceling out when we were simplifying rational expressions. So they cancel, which leaves me with the function in simplified form being x minus 2 over x plus 3. Now, I'm not going to put them in parentheses anymore because these other factors canceled out. Okay? But there's the simplified, and I cannot cancel the x's there because of addition and subtraction signs on the top and the bottom. Okay? So, a vertical asymptote, and I'm going to abbreviate that VA. That occurs when the denominator is equal to 0. So if we look at our denominator here, x plus 3, set it equal to 0 and say, okay, what would x have to be to make it undefined? Well, we subtract 3. So x equals negative 3 would be, or this rational function would have a vertical asymptote at x equals negative 3. Now we'll look at holes. Or does a hole occur? The value of x for a hole. Right here, we had a factor that canceled out. So what you want to do is you want to use the zero product property on that factor that canceled out. So you take the factor that canceled out, which was x plus 2, set it equal to 0. Solve that for x, I subtract 2. So there would be a hole occurring at x equals negative 2. Now, if you actually want to find the coordinate of the hole, the x value would be negative 2. And to do that, then you would plug negative 2 into the function right here, the simplified function. So, now again, they only ask for the x value of any hole, but I'm actually going to find, if we were going to graph it, where the hole would occur. So I would plug negative 2 into this function. I have f of x equals x minus 2 over x plus 3, and I'm going to put my negative 2 in there and in there. Negative 2 minus 2 on the top would be negative 4. Negative 2 plus 3 on the bottom would be 1, so it would be negative 4. All that's finding is the f of x value, which is the same as the y value. So if they actually asked you to graph it, there would be where the hole occurs, negative 2, negative 4. They're just asking for the x value of any holes, so that is really x equals negative 2. Similar one here on the next example. We're going to factor this. Difference of two squares on top, x plus 3, x minus 3. On the bottom, trinomial factoring. I want two factors of 15 that add to 8, which would be 3 and 5, both positive. These two factors cancel. We'll do vertical asymptote first. So the simplified expression is f of x equals x minus 3 all over x plus 5. So to find the vertical asymptote, we want to set the denominator equal to 0 and what makes it undefined. So it would occur at x equals negative 5 for my vertical asymptote. A hole occurs at the factor that canceled. My x plus 3 is what canceled out. Set that equal to 0. Solve. So subtract 3. So it's at x equals negative 3. And again, if I wanted to actually graph this, I would have to find where the hole, at what coordinate the hole occurred at. So I'd put negative 3 into the function right here. And I'll just do the work off to the side here. I'd have negative 3 minus 3 on top, which is negative 6. Negative 3 plus 5 on the bottom, which is 2. If I divide that, I get negative 3. So the hole would actually occur at negative 3, negative 3. Now, they aren't really asking about horizontal asymptotes right now, but let me get into just a brief explanation verbally with you. Horizontal asymptotes occur basically where you look at the simplified expression. So if I had this simplified expression, x minus 2, x plus 3, if I took and looked at the coefficients on my x terms, which is a 1 and a 1, this would mean a horizontal asymptote. If I actually took the 1 and divided by the 1, that means a horizontal asymptote occurs at y equals 1. Okay. Now they're not asking for this in this problem, but I'm going to get into the graphing here and determining that. And you'll be able to see when we do the table function on the calculator. Same thing over here. Notice my simplified expression, I have 1x and 1x. So again, a horizontal asymptote would occur at y equals 1. Okay. They didn't ask for it on these problems, but I'm leading into when we actually have to do the whole graphing. And that's what we're going to do here at the end. To graph rational functions, use the following. Now, find the x value of any holes, if there are any. That's only if something cancels. So we're going to write that here, if something cancels out. In other words, a factor cancels. Find the equation of any vertical asymptotes. That's what makes the denominator 0. We're actually going to involve all this in the xy chart. So we're going to make an xy chart, an xy table, whatever you want to call it, and I'll show you how to actually do that on the calculator here, on your graphing calculator. Those that don't have a graphing calculator, what you'll have to do is actually plug them in to find your y values. Pick some x values and figure it out. Okay, so here's what we have. This is the given function. F of x equals x over x plus 1. Can't cancel the x's. I can't factor anything top and bottom there. That is actually in simplified form. Okay, so it's x over x plus 1. Can't do any simplifying there. So if I look at number 1, nothing canceled, so this particular rational function has no holes. A hole only occurs when a factor cancels. Let's look at vertical asymptotes. Okay, vertical asymptotes occur at when things are undefined. So you want to take the denominator and set it equal to 0 and solve. You're using the zero product property on the denominator. So I would get at x equals -1 is my vertical asymptote. So I know right now if I graph the vertical line, and I would suggest drawing these in as dashed lines, at x equals -1, there's a vertical asymptote. Okay, x cannot be -1 or the function would be undefined. So what you want to do in the middle of your table, when you're actually making a table right now, is you want to put -1 in there. Now, on this, I'm going to put a line, and then behind it I'm going to put, that's where my vertical asymptote occurs. We're making an xy table. I put a line or a dash there, and you'll see this when we pull it up on the calculator, because when we plug -1 in here, we get 0 on the bottom. It's undefined, so you can't do it. That's why there's a vertical asymptote there. So what you want to do is you want to pick some values on either side of it. So I'm going to pick like some less than it, -2, -3, -4, and then I'm going to pick 0, 1, and 2. Now, you could plug each of these in by hand. Some are going to be fractions, figure out what you get. But I'm going to show you on the graphing calculator a quick way to get your table. So let me pull up my graphing calculator, and we're going to put in x, so you go to y equals. So if you're on your regular screen, you hit y equals. Okay, and you want to put in, the only thing I have on top is x, and I want to divide that by x plus 1. Now, x plus 1 has two terms. Very important here when you do this. You must put x plus 1 inside parentheses because there are two terms. Okay, so there, and then hit enter. And now what you want to do is you want to go to your table, which is above the graph key on the 83s or 84s. So I'm going to go second graph, or second table. Notice for -1 you get an error. Okay, here's my table. So notice -1 here, and I'm actually going to scroll up one more and go to -4. So pretty much I get -4, 1.33, which is 1 1/3. -3 is 1 1/2. -2 is 2. Notice -1 right here says error. Okay, 0's at 0, 1's at a half, and basically 2, this is a rounded decimal, is at 0.6 repeating, which is 2/3. So if I actually do that, let's fill those in, and you can have it on your calculator if you actually put it in there. -4, we're at 1.3 repeating. At -3, we're at 1.5, 1.5. At -2, we had a 2 in our table. Now, again, the calculator told me error here. It's because you can't divide by 0. It makes the denominator 0. That's why there's a vertical asymptote. At 0, it's 0. At 1, it's 0.5. And at 2, it's 0.6 repeating. I'm just going to put it as 0.67. So what you want to do is you want to graph these points. So -4, 1 1/3 basically. So you have to estimate 1 1/3. At -3, we're at 1.5. Actually, I probably could be a little lower there. So at -3, we're at 1.5. At -2, we're at 2. Okay. Now let's plot the other ones. -1, I'm at a vertical asymptote there. At 0, we're at 0. At 1, we're at 0.5. At 2, we're at 0.67. We're here. Now, what happens? And this is going to end up being what we call a hyperbola, and I'll show you why. Okay? Even though it doesn't say it here, I'm actually going to talk about a horizontal asymptote. Horizontal asymptote occurs if you look at the simplified expression. And here's what we had. F of x equals x over x plus 1. Can't simplify that any. If I look at my coefficients in front of x, 1 divided by 1 is 1. So basically a horizontal one occurs, horizontal lines are y equals, at y equals 1. We are going to have a horizontal asymptote occurring at y equals 1. What this means is that graph is going to look like this. We're going to come up here, and it's going to get very close to my vertical asymptote and keep getting closer, but never actually touch that as it keeps going up there. And then it's going to come down here, through this point, and keep getting closer and closer and closer to that horizontal, but never actually touch it. Same thing's going to happen on the other kind of kitty corner from it, or diagonally from it. As we go here, we're going to come up and get closer to that horizontal asymptote, but never, now I drew that kind of bad, it never would actually touch it. Same thing down here, it's going to keep getting, as it keeps going down, getting closer and closer to that, and that is actually a hyperbola. That would be the graph of this rational function. And there's what that would look like. Now, if we go back to the calculator, let me show you what happens as you keep scrolling up and down. As I keep going further in my x's, you see how it's getting closer and closer and closer and closer to 1.000, but it would never actually get there. See, I'm all the way down to negative. If I went the other way, I'll just hold this down for a second. And I guess I got to keep clicking on it. If I keep going the other way, if I go to the positives, as x goes to positive infinity, as I keep getting further and further and further out in the positives. Now, if you look here, see how it's getting 0.96, 0.96, 0.97. It's going to keep getting closer and closer and closer and closer to 1, but never get there. Now, I kind of showed you a shortcut way to figure out a horizontal asymptote. And if we actually hit the graph button on the calculator to take a look at what it is, let me check my window here first. And we're going from -10 to +10 by ones. I actually want to change these to negative. Whoops. Let's backspace that a little bit. I actually want to do -10 and then enter, and I want +10. So that just tells me I'm going to go from -10 to +10, and I want to go by ones. And let's hit graph once and see what happens. Now, the graphing calculator doesn't give you a great picture. You can kind of see a vertical asymptote there. Like I said, it doesn't give a great picture, but that is what our graph looks like. Like I said, it doesn't give a great picture or visual picture like mine. All right, I'm going to do the last example on the next video, part 2 here. So I'm going to stop this one.